In the last section, we looked at some differential equations that modeled law of growth functions. And today we are looking at logistic models, which is just another type of relationship involving populations, that sort of thing. So the differential equation, when the rate of change is proportional to the current population, that's the 7.8 differential equation. We know that we have this exponential function as its solution. However, frequently with populations, there's some limiting factor. Like if we're talking about the fish that were in the lake, in that last problem on the previous notes, there's a finite amount of space in the lake, so we can't just have an infinite number of fish. So really, we end up with something that is more of a logistic growth type of relationship. Okay, and so those are the ones we're specifically looking at today. But this is just another type of differential equation that models some kind of growth situation, or potentially decay. Okay, so with the function, this is the differential equation right here. Okay, so with this function, capital L is the variable here that is used to represent the carrying capacity. So that's the maximum population that can be sustained as time increases. In other words, when it asks us for like what is the limit at infinity, it's always going to be that whatever that L value is. And if you think about this, as L approaches, or as T approaches infinity, or forget T for a second, as the population approaches the carrying capacity, then this fraction right here approaches 1. Okay, so this approaches 1, meaning the 1 minus that approaches 0. Okay, and then it doesn't matter what the population or the constant are, because if the rate of change is going to be something times 0, which means the rate of change is 0, meaning we have a horizontal tangent, and so that's going to be that carrying capacity. If you remember, a logistic growth function kind of looks like this. Okay, and we have two asymptotes. We have a horizontal asymptote going towards positive infinity. We have one going towards negative infinity. Okay, so whatever that value is, whatever this height is, that is going to be the carrying capacity. Okay, the logistic growth equation that comes with this differential equation is written right here. This is never something that you are going to have to be able to solve for yourself. You'll see in an example here in a minute that if we're using that, it's going to be given in the problem. If you want to try and obtain this yourself, you're welcome to do so. So to solve that differential equation, we would divide everything by the y and the 1 minus y over L, and then multiply by dt. So we would have 1 over y times 1 minus y over L, dy equals k dt. And then when you integrate both of these, you have to use partial fractions on this side. Remember, L is a constant, so you use partial fractions over there. You can multiply everything by L to get rid of the fraction. You can do it if you want. You don't have to. All right. So no matter how this is written, either as the solution or as the differential equation, L is our carrying capacity. Okay. So when will a logistic growth curve reach half of its carrying capacity? This is frequently a question that comes up when logistic growth is involved. And that is going to be at half, because the logistic growth function has symmetry around this point right here. This is an inflection point. Okay, so at the inflection point, at the inflection point, when we are changing from concave up to concave down, meaning the second derivative, so d squared y over dt squared is equal to 0. Okay, so if you're asked a question about, like when the second derivative equals 0, what is the what's the population or something like that, then it's going to be half of the carrying capacity, or vice versa. Okay, so let's look at a few questions. So for the first one, again, we have logistic growth function, and it says find the solution to the logistic growth model for the differential equation that's given. This is just, that was something when I took a screen clipping. It was a cursor. So we have dy over dt equals 2y times 10y minus y. Now this one's written slightly differently from this form right here, okay? But we can get it into this form by dividing everything by 10. I'm picking a 10 because I want this value right here to be a 1. Okay, so I'm going to do that first, and then I'll deal with my initial condition. So dy over dt is going to be 2y, no, that's a t, 2y, and then I'm going to write this as 1 minus y over 10. But here's the thing, if we divided by 10 right there, we really need to factor that 10 to the outside. So I'm going to change this to be a 20. Okay, I'm going to change that to be a 20. All right, so there's my differential equation. Okay, and then we can also use our initial, nope, not yet. We can use our general solution. Okay, so we know it's going to be something in the form y equals, and then the carrying capacity is 10, because remember that's in this spot right here. So 10 over 1 plus b e to the negative kt, and we don't know what b and t are yet, and that's okay. We need to find those. Okay, so right off the bat, we can eliminate, let's see, we can eliminate this because of that 11 situation right there. Okay, all right, so now let's look at our initial condition. So we know that y of 0 equals 1, so the ordered pair 0, 1 is t comma y. Okay, so I'm going to plug that into this. Okay, so 1 is equal to 10 over 1 plus some value of b times e to the, okay, we know the k value as well, because k is the variation constant here, which once we wrote it in this form, it is a 20. Okay, so we need a 20 right there. So negative 20 times 0. Now, I mean, it's still going to be 0 here, but we do know the k value. Okay, so then we end up being able to solve for b. So this right here is just a 1. And then I'm going to multiply both sides by 1 plus b. So we have 1 plus b equals 10. And then we can subtract 1. So b is equal to 9. Okay, so our final solution, our general solution, is going to be 10 over 1 plus, and then we have a positive 9. So 1 plus positive 9. Okay, so this is out. And then we need a negative kt as our exponent, so it's this right here. So B is our answer. All right, for the next one, okay, and at any time, definitely pause these and try them yourself and then see if you get the same thing, okay? But so here it says the number of phytoplankton specimens is increasing according to the logistic growth model. Which of these statements could be true? Okay, so we want to see which one of these will represent being modeled by logistic growth. Okay, so I'm just going to go through and explain why we eliminate each of them. This is the one that jumps out at me first. This is a law of growth because it's the rate of changes is proportional to the current population, so that is out right away. Okay, this one right here, the second derivative being positive, that is false, because if the second derivative is positive, that would be concave up, but we know that we switch to concave down once we hit half of that carrying capacity, so that is going to be out. Okay, this one right here is out because I need a negative value right here in order to have a logistic growth. Remember, that function should look like this right here where we have negative kt. Okay, so that is out. This one right here is the logistic growth function. And one of the reasons I know that is because I have the population and then a constant minus the population. If you think about, like, we could divide this whole thing by 1780, we would have a 1 minus p over 1780. So that tells us what our carrying capacity is, and then the 1780, if we factor that out, we could just multiply it to the other side and it could be part of, you know, this constant that gets integrated. But this is the one that does match this formula right here, okay, our logistic growth form. So that is our correct answer. Okay, and then another one here. So, okay, here it doesn't say in words that this is logistic growth, but we do need to recognize that this is logistic growth. We have, anytime you see this right here, okay, like 1 minus a variable over a constant, or the constant minus the variable, something like that, something where the derivative can approach 0, then, and that it's being multiplied by another variable, that is going to be an indicator that it's some form of a logistic growth. Okay, so when I look at this, I do need to recognize that that's logistic growth, and I see the G out here and then the 1 minus G divided by 64. Okay, that tells me that my carrying capacity is 64 as well. Okay, so my carrying capacity is 64. All right, and the question says, for what value of G is the extraction rate increasing the fastest? Okay, so, I mean, what we could do is we could find the second derivative. If you're doing that, I would distribute this and then take the derivative with the power rule instead of using product rule. And then you set that equal to 0, etc. But what will you really get? We're going to get that this is faster, that it's increasing the fastest at half of that rate. Okay, so this is one where even if we don't recognize that it's logistic growth, we could get to the answer by finding the second derivative. So take the derivative of this, set it equal to 0, etc. Solve that. But it's faster just to recognize, hey, that's my carrying capacity, and I know that it's the rate is increasing the fastest at half of that value. Okay, last one here. Conservation, let me make that a little small. Okay, conservation organization releases 30 panthers into a preserve. After 3 years, there are 50 panthers. Okay, so that's a data point. So 3 years, 50 panthers. Our times 0 is going to be 30 panthers, and then the carrying capacity is 150. All right, this is a logistic growth function. Once again, we recognize that form, and it gives us the solution. So first question, find the carrying capacity. Okay, our carrying capacity, it tells us, is 150, which is the value that goes right here. So there's that one. Okay, to solve for B, we can go ahead and do that. So let's start with, we're going to have to figure out what K is as well. So let's start with the initial point 030. Okay, so I'm going to do 30, might need more room here. 30 is equal to the carrying capacity over 1 plus B times E. And actually here it doesn't matter what K is because our time is 0. So we get, let's see, I'm going to divide both sides by 30, make that a 1, make that a 5. Okay, so then 1 plus B times 1 is equal to 5. So B is equal to 4, okay? And then for part C, we are going to use the other ordered pair, 350, and plug that into our solution. So we've got 50 equals 150 over 1 plus, and we just determined that B is 4. So 4e to the negative k times 3. Okay, I'm going to reduce this again, make that a 3. All right, so now this denominator has to equal 3. Okay, so I've got 1 plus 4 e to the negative 3k equals 3. So subtract 1, divide by 2. So e to the negative 3k is equal to 1/2. Take the natural log. So negative 3k is natural log 1/2. Divide both sides by negative 3. So we get k equals natural log of 1/2 all over negative 3. Or that negative, if we put that right here, then we can write that as natural log 2 all over 3 because I can make that negative, this exponent up here, and then 1/2 to the negative first. It doesn't really matter. If you write something that is numerically equivalent, it's going to be fine, but this is the most simplified form here, okay? So natural log 2 over 3 is our exact value for k, all right? And this is probably a no calculator question, so that's why we want an exact answer. Okay, then write a model for the population. This is asking us to plug the values we just found back into this solution right here. So that is going to be P equals the carrying capacity, 150, divided by 1 plus, and then B is 4, and then e to the negative natural log 2 over 3 times t. If you want to simplify that, you can. We have 150 over 1 plus 4, and then that would be the e to the negative natural log 2 part. Actually, I'll just keep the negative with the t and the 3. So e to the natural log of 2 is going to be just 2, and then, let's see, so times 2, but then we still have e to the negative t over 3 left over. Okay, so if you want to do that, you can, but you can also just stop right here. Okay. And that is in terms of t. Okay, so then for the last one, it says, oh, no, I'm sorry, next to last, it says use this model to estimate the panther population after 12 years. So now we're plugging 12 in for t. So population is 150 over 1 plus 4 e to the negative natural log of 2 over 3 times 12. Okay, which that becomes a 4. So we have 150 over 1 plus 4 times e to the negative natural log. No, I'm going to keep the negative with the 4. So now it's, here, we'll do it this way. It's now negative 4 natural log of 2, which is 150 over 1 plus 4. Okay, so that is e to the, and you can do this in one step. You don't have to write out, 2 extra steps. I'm just doing the arithmetic part. So we have natural log of 2 to the negative 4th. Okay, and then that's going to cancel out. So 150 over 1 plus 4, and then 2 to the negative 4th would be 1/16. So 150 over 1 plus, that's 1/4. Let me change this to a 5/4. So let's divide 150 and 5 reduces to a 1 and a 25. Nope, sorry, 15. So 15 times 4, which is 60. Okay, last thing before my laptop dies. Sorry, this video is long. Probably should have cut it into 2. What's the limit of the model as t approaches infinity? It's just asking us to recognize carrying capacity. So that is 150.